Hello, hello. I'm going to see if I can tackle all the material I want to tackle in 15 minutes because that's how long YouTube gives me. Okay, we're in Jacob's Geometry chapter 4, lesson 5 this week, the isosceles triangle theorem. Okay, so let's talk about that. You all remember what isosceles means, that it's a triangle that has to have at least two equal sides. I think in class that I had said it exactly two equal sides. But then I thought about it afterwards, and it's at least two equal sides. So an equilateral triangle is technically isosceles also. Little tidbit. Okay, so the very first, this one's heavy on theorems, so let's get to them. If two sides of a triangle are equal, then we know, here's my lovely little triangle. Here's my two equal sides of my triangle. And now we're going to learn something about that. One thing that this is going to immediately trigger from now on is that if those two sides are equal, then these angles too must be equal. Okay? So if two sides of a triangle are equal, then the angles opposite them, can't really spell today, must also be equal. All right, so that's the first theorem we've got. So I want, as soon as you see a triangle that looks like this with two equal sides, I want you to immediately just go bing, that means the angles opposite them are also equal. All right, now this leads to something called a corollary. Corollary is a separate theorem that is so easily proven by this theorem that it's not even, it's just given this special name because the two are so closely related. Okay, so this is the corollary to that. And this, oh, actually, you know what? Maybe I should walk you through how to do this one. Okay, just real quickly through the proof. We're not going to do the whole thing. So if two sides of a triangle are equal, then the angles opposite them must be equal. Now, one cool thing that actually I really like how Jacobs introduces this in this section. He talks about Alice in Wonderland and Through the Looking Glass. Now, the cool thing about this is that if you picture it like Alice pictures it through the looking glass, if I called these, I think in the book he did D, E, F. So I'll try to stay close to what he did so that it's easier for you to follow. This proof is listed in this lesson, so feel free to look through it on your own. Now, what he does is he creates a new triangle. Oh, and I don't have enough paper to do it. Well, he basically creates the mirror image of that triangle, okay? Except what he does is he flips it. So F now goes over here, and D goes over here. In order to prove it, you can see probably pretty easily how it works. The two sides of the triangle are equal. And if you create this new sort of ghost, sort of looking glass triangle, then you know a few things. You know that these sides wind up being equal to these sides. And you know that E is equal to itself, right? So in this, if this ghost triangle is here, then it must be congruent to this one because the sides are equal and that angle at the top is equal. So because of SAS congruence, then you know that these two triangles have to be congruent. And that means that these two angles down here are also equal to these two angles over here. And so that means that that D winds up equaling F, D equaling F. And so you can show that those angles, D and F, have to be equal to one another. So, like I said, look through the book if you want to follow that proof a little more closely. Okay, next one though, the corollary to that one says that if a triangle is equilateral, and I've drawn one here, it is also equiangular. Now, equiangular means that all three angles have to be equal. So the way we're going to prove this is just use that last theorem. That last theorem said that if the sides are equal, then the angles opposite them are equal. So let's see, let's look at, let's call this one, we'll just call this one DEF also. Okay, so if you're looking at those two sides, then you know, because of the last theorem, that the angles opposite them are equal. But let's turn it a little and consider these two sides instead. Then we know that that angle is equal to this angle. So since that's what that one is, that third one must also be equal. Okay. Once again, it's a quick proof. That proof is also listed in that lesson in the book, so feel free to look through it. But I think you can see intuitively why, knowing that the opposite sides must be, or excuse me, the opposite angles must be equal, why it makes this triangle equiangular. Okay, so now, so that was the first theorem and the first corollary in the section. There's another theorem and another corollary, and the crazy thing is, this next theorem is actually, here, let's look at it. The first theorem we learned, if two sides of a triangle are equal, then the angles opposite them must be equal. This one is, if two angles of a triangle are equal, then the sides opposite them are equal. Can you see how those are related? I hope so. I hope you can see that these two are converses of one another, which is unusual, right? We don't normally get, normally the converse of a statement isn't really true unless it's a definition. But in this case, we can prove it. We can prove it fairly easily. I'm going to do that. Yeah, we'll prove this one together in just a second. What it's trying to say is if two angles of a triangle are equal, let's pick any two, since those appear to be equal. So let's use those. So if two angles of a triangle are equal, then the sides opposite them are also equal. So that's handy dandy. And it should be another one of those triggers. As soon as you see two equal angles within the same triangle, you should know that the sides opposite them, your eyes should immediately go to those sides. Okay, so we'll prove that one in a second. I'm going to set that one aside. The corollary to this one, not surprisingly, if a triangle is equiangular, it is also equilateral. And I'm going to have you prove that one for homework. So let's go through the proof of this one together. See how efficient I can make it. Oh. Okay. So once again, the theorem is if two angles of a triangle are equal, the sides opposite them are equal. Okay, so I've got these two triangles here. I did the same thing. Okay, I created this ghost triangle. All right, it's the same one. It's just the looking glass version of the triangle. Pretty handy dandy technique because we know all of these ways to show two different triangles are congruent. So if we can use those, then we'll be able to show that the other parts are equal, which is convenient. Okay, so what are we trying to show here? We're trying to show if two angles of a triangle are equal. I've got them right here. If D and F are equal, then we're trying to show that ED and EF are also equal. Okay, so what are we given? First thing we're given is triangle DEF. So I'm just going to say, so let's go. In triangle DEF, these two angles are equal. So the measure of D is equal to the measure of F. Okay, so that's all we're given for this one, period. What are we trying to prove? We are trying to prove that the sides opposite them are also equal, right? So we're trying to prove that DE equals FE. Dot. All right, okay, so for any proof, we're going to go ahead and start with as you know, the given. Okay, we'll say in triangle DEF, The measure of D equals the measure of F. Reason? Given. Perfect. Step 2. Okay, so since we know that angle D is equal to angle F, let's think about our strategy for this. If we've got these two triangles, if we can show we've got these angles, so if we can show that this is the same as that, then we've got it, right? Then we've got angle side angle congruence. Okay, so let's do it. Let's go ahead and do the next step is step 2. Let's show that DF is equal to FD, and this is everybody's favorite. Everybody's favorite. Just like looking in a mirror, obviously DF is the same as FD, so we're going to use the reflexive property for that one. Okay. Now we've got we have shown now that that is equal to that. The only other thing we need to do, I think, is equal to F. So technically, we've only shown D equal to F. We haven't shown F equal to D yet. Okay, so let's go ahead and do that. And that way we'll really have angle side angle. So we'll do F is equal to angle D, and you can get that from this step right here. All you need to do is switch them. That's called the symmetric property. Great. So now we've shown that triangle DEF is congruent to triangle FED. And the way we've done that is by identifying two sets of angles and two sides to the included side. So that's called angle side angle postulate. Okay, and we were trying, remember, to show that DE is equal to FE. Now we've got it. The two triangles are congruent, therefore its corresponding parts must be equal. Okay, so we've done it. We've proven what we wanted to show. Two triangles are congruent. You must be feeling very accomplished. Their corresponding parts are equal. That's my little shorthand. You've done it, QED. That's it. Hope you guys are having a great week. I can't think of anything else. I will, if you have any questions, let me know. Otherwise, I'll see you on Friday. Homework is going to be set 1 from lesson 5. Set 1 from lesson 5. And in addition, I'd like you to do number 28, which proves the corollary to Theorem 14. That's it. Take care.